Here's a question that sounds almost too simple until you try to answer it honestly. When one object affects another, how does that influence actually travel? Not what happens, but the mechanism behind it. If I push a book across a table, the story feels complete. My hand touches the book moves, and the chain of cause and effect is obvious. Contact makes sense to us because we can picture it. But now make the situation only slightly less familiar. Bring a magnet close to a piece of iron. The iron slides toward it. No contact, just open space between them. Yet something clearly crossed that gap, because the iron changed its motion. So the hard question shows up immediately. What moved through the empty space to make that happen? For a long time, people avoided staring at that question too directly. The old view was comfortable. Objects influence other objects directly. Something reaches out and pulls. But once you slow down and demand a real mechanism, that picture starts to shake. How does the magnet know the iron is there? Does it send a signal? If it does, how fast does it travel? And what exactly carries it? Magnets were not the only place where this problem appeared. Gravity had the same issue. Earth pulls the moon, the sun pulls Earth, and every mass seems to pull every other mass. But how? Isaac Newton, who gave us the law of gravity, was famously unsettled by the idea that one object could act on another across empty space with no intermediary. He could calculate perfectly and predict motion with incredible success, and then admit he didn't know the deeper cause. Gravity worked well enough to compute orbits, but the underlying process still didn't feel like an explanation. That gap between being able to compute something and truly understanding it runs through physics again and again, and the idea of a field was created specifically to close that gap. To understand why, it helps to step back and rethink what we mean by empty space. We usually call space empty when there's no matter in it. No atoms, no dust, no air. But is that the whole story? Could space itself have properties even when there's nothing inside it? Imagine putting a small test object in space, like a tiny charged particle, at a particular point. Then you watch what happens. If it accelerates, something must be acting on it. You didn't place another object nearby, so instead of saying a distant charge is somehow pulling on it through nothing, you can say something different. Space at that location is in a particular condition, and that condition determines how the particle moves. That is the first core idea behind a field. A field is not a thing sitting in space the way a rock sits on the ground. A field is a description of the state of space itself. At every point, you can assign a quantity, maybe just a number, maybe a direction, maybe both, that tells you what would happen if you placed the right kind of object there. In an electric field, the value at a point tells you the force a charge would feel. In a gravitational field, it tells you the acceleration a mass would experience. And the object doesn't need to be present for the field to exist. The field is already there, quietly defined everywhere. This shift may sound small, but it changes everything. Instead of saying the sun pulls on Earth, you say the sun changes the gravitational field around it, and Earth responds to the field at its own location. The interaction stops being a mysterious long-distance reach. It becomes local. Earth reacts only to what is happening right where Earth is. That matters because nature seems to insist on locality. Nearby things influence nearby things, and any influence takes time to spread. A field makes that possible. If the sun were to suddenly vanish, a strange thought but useful, the change in the gravitational field would not be felt everywhere instantly. It would travel outward at a finite speed. Space would adjust point by point, and only then would distant objects respond. And that is where the modern story really begins. Historically, this idea didn't appear in one clean moment. It grew slowly, pushed forward by experiments that refused to fit the older picture. Electricity is a perfect example. Early observations showed that charges attract and repel in a way that looks similar to gravity, stronger when close, weaker when far. It would have been easy to stop there and declare, fine, another action at a distance force. But experiments didn't stay simple. Moving charges produced magnetic effects. Changing magnetic situations produced electric effects. The forces weren't just stronger or weaker, They had direction. They could twist needles, create patterns, and induce currents. Something detailed and structured was happening, not only at the charges themselves, but throughout the space around them. So physicists began paying attention to the region in between. Imagine filling the area around a magnet with tiny compass needles. Each needle turns to point in a specific direction. If you draw arrows showing how they line up, you've made a map of the magnetic field. That picture reveals something important. The field is not the magnet. The magnet is the source, but the field is what exists throughout the surrounding space, with its own shape and structure. You can build intuition for this by thinking about something even more familiar: temperature. In a room, the temperature can vary from place to place. You don't need a thermometer at every point to say the room has a temperature field. The thermometer just reveals what is already true at that location. In the same way, a charged particle or a mass can act as a probe. It doesn't create the field by being there. It simply shows you what the field is doing at that point. That analogy matters because it makes the idea less mysterious. We already accept that space can have properties, warm here, cooler there, without needing a physical object sitting in every spot. A field extends that way of thinking to motion and forces. But then a deeper question arrives. Is a field only a mathematical tool, or is it physically real? At first, many people hoped it was mainly a convenient bookkeeping device. If you have many charges, calculating every pairwise force becomes messy. But calculating one field and then asking how each charge responds is cleaner. That's efficient, and it feels like a smart trick. Over time, though, experiments began to show that fields aren't just a trick. Fields carry energy. They carry momentum. They can vibrate, and they can exist in regions where there are no particles at all. Light turned out to be the clearest example. Light is an electromagnetic field moving through space. Once it is created, it does not require charges to keep escorting it along. The field itself oscillates and travels. That realization was astonishing because it changed what nothing means. Empty space, once treated as a passive stage where physics happens, turned out to be able to support waves, store energy, and transmit influence. Space wasn't just an arena. It became an active participant in the story. At this point, it's tempting to ask what the field is made of. Is it a hidden substance? A medium? A thin, invisible material filling the universe? This is where physics has to be careful, because history shows how easy it is to force new ideas into old habits. People once proposed a substance called the ether, a material that fills space and vibrates to carry light waves, the way air carries sound. But that idea ended up being unnecessary and misleading. The field does not need to be made of anything in the ordinary sense. It is treated as fundamental. Asking what a field is made of may be like asking what numbers are made of. The more useful question is not philosophical composition, but behavior. What does the field do? How does it change? And what rules describe it? Physics advances by discovering reliable laws that connect what we observe, not by guessing a hidden substance behind every concept. So focus on what fields let us do. They replace mysterious distant influence with local interaction. They let change propagate through space at finite speeds. They unify electricity, magnetism, and light into one framework. And they force us to rethink emptiness itself. But even with all that clarity, something still feels unsettling. If fields exist everywhere, then the universe is never truly empty. And if particles are things that respond to fields, or are sometimes excitations of fields themselves, then maybe particles aren't the deepest layer after all. That thought pushes us toward a bigger idea, one that reshaped physics in the 20th century. If space can carry structure, energy, and influence, if it can have a condition at every point, then we're forced to question something we usually treat as obvious, that objects are the universe's basic building blocks. Our instincts tell us the world is made of little pieces of matter. We imagine particles moving around, bumping into each other, pulling and pushing through forces. In that picture, fields feel secondary. Useful, yes, but not as real as the particles themselves. Here's the uncomfortable twist. Modern physics quietly reverses that order. Instead of saying particles come first and then create fields, it turns out to be more accurate to say fields come first, and particles are what we observe when fields behave in certain localized, quantized ways. That's a strong claim, so it's worth approaching it slowly, step by step, and seeing how nature pushes us there. Start with waves on water. A wave is not a separate object riding on top of water. It's a pattern in the water. If you ask what a wave is made of, the answer is water, because the wave is the water moving in a particular organized way. And importantly, the wave is not a chunk of water traveling across the ocean like a drifting log. Most of the water mostly stays in place while the pattern moves. Now imagine a sharp, localized ripple moving across the surface. It can look like a thing. It can even feel like an object. But it still isn't a separate piece of water. It's a structured behavior of a continuous medium. Fields behave in a surprisingly similar way. An electromagnetic field fills space. When it oscillates in a certain pattern, we call that light. When the oscillation is localized and quantized, when it can only exist in discrete packets, we call those packets photons. The key point is that the underlying entity remains the field. So when a photon is detected at a point, what you're witnessing is not a tiny billiard ball arriving there. You're seeing the electromagnetic field interact with matter in a discrete way. This isn't just a philosophical preference. Experiments force it. In quantum physics, what we call particles don't behave like tiny solid objects moving along clear, definite paths. They spread out. They interfere with themselves. They show wave-like behavior until the moment they don't. The only description that consistently works is one where the fundamental entity is a field defined everywhere, and a particle is an excitation of that field. In that framework, every type of particle corresponds to its own field. There is an electron field, a quark field, a neutrino field. Even the vacuum is not emptiness. It's what you get when all these fields are in their lowest energy states. That's why the language of fields becomes unavoidable. You can try to avoid it, but the mathematics and the experimental results pull you back. This leads to another crucial point. Fields are not static backgrounds. They are dynamic. They evolve with time, interact with other fields, and most surprisingly, they can fluctuate even when nothing obvious is happening. A quantum field is not perfectly still, even in its lowest energy state. It jitters, not because something external shakes it, but because the laws of nature don't allow it to be completely motionless. This isn't measurement error or random noise. It's built into the structure of quantum reality. So when physicists say vacuum, they do not mean nothingness. They mean the ground state of all fields, a condition with structure, energy, and measurable consequences. That idea explains something that would otherwise seem impossible: how particles can appear and disappear. Under the right conditions, if you supply energy to a field, that energy can show up as excitations, particles, coming out of what we once called empty space. Later, those excitations can disappear back into the field. Nothing is being created from nothing. The field was already there. Notice how different this is from the old mechanical worldview. Instead of a universe built from tiny solid parts, we get a universe built from continuous entities, where discreteness emerges in the way fields can be excited and how we observe those excitations. It's natural to feel uneasy here. Fields are everywhere, invisible, and not something you can hold or point to in the usual way. Yet physics asks us to treat them as the deepest layer of what's real. So how do we know we're not just inventing a clever story? Because fields do something essential. They make precise predictions that object-only theories cannot replace. They tell us how fast influences travel. They explain why electromagnetic effects move at the speed of light. They predict waves, radiation, and interference patterns that experiments confirm with extreme accuracy. And when we try to remove fields and talk only about particles interacting directly, the mathematics often becomes inconsistent or collapses. Fields aren't optional. They are the language nature uses. Now, bring gravity back into the picture, because it completes the story. Gravity was the first force we ever learned to describe with a precise equation, yet it was the last to fully fit into the field viewpoint. For centuries, it looked like a simple attraction between masses, a pull that somehow stretched across space. But as physics advanced, that explanation stopped being satisfying. Experiments and theory slowly pushed us towards something deeper. Instead of thinking of gravity as a force reaching through space, we now understand it as a property of space itself, its geometry. Mass and energy change the structure of space-time, and objects move in response to that structure. Once again, the influence is local. Nothing sends out an invisible rope that tugs from afar. An object simply responds to the condition of space-time where it is. In this sense, gravity is not really a force in the old sense at all. It is the behavior of a field, one that determines what straight paths are and even how time flows. So whether we are talking about electricity, magnetism, light, or gravity, the message converges on the same point. Space is not an empty stage. It has properties. It evolves. It carries structure. And once you accept that, you reach a turning point in how you think about the universe. If fields exist everywhere and particles are excitations of those fields, then reality begins to look less like a machine built from separate parts and more like a continuous system shaped by rules rather than pieces. That doesn't make the universe vague. In fact, it makes it more precise. Fields obey exact equations. Their behavior is tightly constrained. They don't act randomly. They follow consistent laws. But this perspective changes the questions we ask. Instead of asking which objects are interacting, we ask which fields are present and how they are configured. Instead of asking what force travels across a distance, we ask how the field changes from one point to the next. When you start thinking this way, many mysteries stop feeling mysterious. They become natural consequences of the structure of space itself. And this brings us back to where we began. We started with a simple discomfort. Objects seem to influence one another across empty space, and no one could quite explain how. That discomfort turned out to be a clue. By following it carefully without hiding behind familiar language, we were led to a quiet but radical idea. Space itself is not nothing. It has structure. It has conditions. It can carry influence. A field is simply the name we give to that structure. This realization reshapes how we think about matter. Particles stop looking like tiny solid actors pulling strings from afar. They become localized events, quantized behaviors of underlying fields. Matter is no longer the starting point. It is something that emerges. What we thought were objects turn out to be patterns. Far from making the universe less real, this makes it more unified. The same framework explains magnets, light, gravity, and the shape of space-time itself. The same idea that describes empty space explains why it is never truly empty. What once seemed like separate phenomena becomes one connected picture. And maybe the most important lesson here isn't technical at all. It's about understanding. Nature does not shape itself to match our everyday intuition. It does not arrange reality to fit our preference for solid things and simple pushes. But it does offer something better than familiarity. It offers consistency. If we follow the logic carefully and accept ideas that feel strange at first, the pieces fall into place. So the next time you imagine empty space, remember this. You are not looking at nothing. You are looking at the most fundamental arena of reality, active, structured, and quietly doing the work that holds the universe together. And once you see that, the real question is no longer what objects are made of. It is what kind of universe makes fields possible at all.